So this video is a short demo to show you how to make a wall thickness analysis or a thickness mesh analysis. So what I have is a benchmark additive manufactured component. This is a part which it's an aluminium material, and it's been intentionally used here because of a number of defects. Typically, you want to scroll through the part like this with a good contrast, and you want to see internal channels having, if there are powders inside, for example. If you go on Windows Leveling, which is the contrasting tool, you can select this little auto contrasting box and drag it to enhance the contrast in the areas of interest. Press the escape key to get out of that mode and zoom in to evaluate that. So you can also search through the object. Let's just make it a quad view. So in a quad view, you can then select any of these orthogonal views. And if your object is not nice and orthogonal, if it was scanned at an angle, then you can use the rotation, translate, rotate tools, which are found here. So you can turn your object within the coordinate system to get it nice and square in your views, and allow you to search for example, cracks which might be present. There are also some pores present. So unintentional pore spaces present. So what I want to demonstrate here is not any of this. I want to demonstrate a wall thickness analysis. This is a benchmark part with different thicknesses of features. Let me just show you the part briefly with a shortcut thresholding tool here. So this is a volume render of this part, and you see there are some specific overhang parts and walls and cylinders of hollow cylinders and solid rods. So the default grayscale render is not so great. I like to use the aluminium preset. It's quite a nice default set of render parameters. You can also modify that slightly to make it more shiny. What we're going to do here is not play with the default rendering. We're going to make a thickness mesh. So in order to do that, we look at this object in one of the 2D views. Let's take this one, for example, and we want to make a segmentation. So we're going to use the define range upper OTSU to define the material of interest that we want to apply a thickness mesh to, or thickness mapping. So what we can do is, if we look through the data, we might find some loose particles on the outside of the part which have been scanned together, or this might be noise particles, disconnected sections. So what we do to remove that, I don't see it immediately here, but I don't want to waste time searching for it. I know they are present. So in order to simplify that, we just go to refine region of interest, process islands. So in this case, we're going to keep by largest. So we keep the largest region of interest, the one largest connected section, which is the material. Also, to simplify the mesh and thickness mapping, we don't need these little pores, which you see here in the, or we can put this define range off. In there, we see powder filled channels. To simplify the meshing, we don't need a mesh at that point, so we can do a fill inner areas 3D. This is this function here. So just to fill that in, and then there's less mesh to be generated. So what we're going to do now, we've got our region of interest. So what we do is, on the left, we go to export a thickness mesh. So we're going to use a normal one. We're not going to downsample this at all, but we can perform smoothing once just to get a slightly smoother surface render. What this calculation now does is, at each surface point, it's calculating the diameter of the sphere that touches the surface point and any other surface. So it's equivalent to the sphere-based thickness volume mapping, but it's giving you values only at surface locations. It's much faster than full volume mapping also. So the algorithm works faster. So, but the larger the data is, the longer it still will take, but it's quite a reasonably fast process on most data sets with a very nice result. So we're almost done. So we've now got a thickness mesh. It's not visible yet, so we need to click on this little eye to make it visible. We see the contour and it has a color map associated with it. If we look in 3D, we can we can visualize the 3D, click on the 3D button and put the volume data off, and we have a nice 3D render. In order to change that view, we can also go to our camera, use lighting or not, and change render settings. I like to use a color map or a temperature mapping, which gives you a nice bright color map like this. So what we have here is we can change this. We can call this wall thickness. So it's the wall thickness locally at each point, and it says the thickest parts are about 12 millimeters. So these thin parts, blue, are approximately 0.5 millimeter, and there you have your own. You know how to make your own wall thickness analysis in Dragonfly. So I hope you find that useful, and see you next time.